Hello everyone. Let's travel back in time to Sir Isaac Newton's laboratory. While observing the image of a distant heavenly body through a lens, he noticed something strange. The edges of the image were colored. At first, Newton thought, oh no, maybe the lens has a defect. But being the curious scientist he was, he polished a lens to perfection and tried again. Guess what? The colored edges were still there. That's when he realized the fault is not in the lens, but in the very nature of white light itself. So, what exactly is white light? To our eyes, it looks plain and colorless, but in reality, it is a clever mixture of many colors hidden together. Each of these colors corresponds to a different wavelength. Violet, indigo, blue, green, yellow, orange, and red, VIBGYOR, all travel together in air at the same speed. But inside glass, each one behaves differently, like sprinters running on different tracks. This unequal speed is the key to their separation. This brings us to a magical phenomenon called dispersion. Dispersion is simply the splitting of white light into its component colors by refraction through a prism. Why does this happen? Because the refractive index of glass, nu, depends on the wavelength, lambda. Violet light, with a wavelength of about 4000 angstroms, travels the slowest and bends the most. Red light, with a wavelength of about 8000 angstroms, travels the fastest and bends the least. In words, the refractive index mu for violet is greater than the refractive index mu for red, which means the deviation delta for violet is greater than the deviation delta for red. That's why the prism doesn't give us a single beam of light, but instead a rainbow-like spread called the spectrum. Picture this, a simple triangular prism sitting in the path of white light. The incoming ray enters, bends at the first surface, and then again at the second surface. But here's the twist, different colors take slightly different paths. By the time they emerge, violet is at the bottom, red is at the top, and all the other colors line up in between. When these rays fall on a screen, we see a beautiful band of colors, the spectrum. This is literally a rainbow you can create on your desk with a prism. According to Snell's law, the refractive index mu is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. In glass, the refractive index mu for violet light is greater than the refractive index mu for red light. That means the refraction angle for violet is smaller and the refraction angle for red is larger. Now, the deviation delta is equal to the angle of incidence plus the angle of emergence minus the angle of the prism. Since the refraction angle is smaller for violet, its deviation delta violet becomes larger. For red, the refraction angle is larger, so its deviation delta red is smaller. In simpler words, violet is like a gymnast, bending sharply. Red is like a strong sprinter, keeping straighter. This is why violet always appears at the bottom of the spectrum, while red always appears at the top. Let's wrap this up. Newton proved that the colored edges he observed were not lens defects but the true nature of white light. Dispersion is the splitting of white light into its colors because refractive index depends on wavelength. Violet bends the most, red bends the least, and this produces the beautiful spectrum we see in prisms, rainbows, and spectrometers. So, next time you see sunlight scattering into colors through raindrops, glass, or even soap bubbles, you'll know it's nature's way of reminding us white light is never plain, it's a hidden rainbow waiting to be revealed. See you in the next session.